So electron energy and position are complementary. We were talking about the uncertainty and the velocity and the position. Velocity is related to the energy of the electron. Because the equation for kinetic energy equals 1/2 the mass times the velocity squared. So kinetic energy is related to velocity. The energy and the position are complementary. So we can't know the energy of the electron and its position at the same time. If it was traveling in a nice circular orbit, like the Earth orbits the sun, we would be able to know both of those at the same time. So we can't describe the electron as being in an orbital. The best we can do is to think about a probability distribution, a region of space in which the electron is probably found. And this is called an orbital. An orbit is just like the planetary system. It's a specific path. An orbital is different. It's a probability distribution. Properties of atoms are often tied to the energies of the electrons. And so this is an important thing to understand. We actually care a lot more about the energy of the electron than exactly where in the atom it is. So we talked about Schrödinger's cat. Schrödinger also has an equation. And this is his equation. And I believe this is capital psi. That represents a wave function. And this math gets into some really hairy stuff. It's calculus and beyond, and so we're not going to do the math here. We're just going to talk about it. This equation, as simple as it looks, allows us to calculate the probability of finding an electron within a particular location based on the amount of energy that it has. And so solutions to this equation give us many different wave functions that describe the wave-like nature of the electron. So if we plot psi squared, that wave function squared, in three-dimensional space, that represents an orbital, a region of space in which the electron is likely to be. So in trying to solve this equation, they found that there are 4 different numbers that are important, and these relate to the size, the shape, and the orientation in space of the orbital. Because we know that the energy of the orbit of an electron is quantized. It can only be certain amounts. And so we have to add something into the wave functions that gives us quantization. And so these are called quantum numbers. So we have the principal quantum number is symbolized with a lowercase n. We have the angular momentum quantum number, that's a lowercase l. And the magnetic quantum number, that's m sub l. And then there's a 4th one, the spin quantum number, and that's m sub s. So L is angular, m is magnetic, and that's related to the angular momentum. And here's the spin quantum number, it's got a subscript of s. So we'll talk about each of these quantum numbers. The principal quantum number, that's the main quantum number, n, is going to be an integer, and it describes the overall energy and the overall size of an orbital. This is analogous to Bohr's energy levels, the different orbits. We had that n equals 1, n equals 2, n equals 3. So it's similar to that, but not really. So n can be any integer, 1 or greater. The larger the n, the more energy, and the larger the orbital. So for hydrogen, we can use the Rydberg equation, a variation of it, and actually calculate the energy of each level. So the energy of an electron in this level is equal to minus 2.18 times 10 to the minus 18 joules times 1 over n squared, where n is the principal quantum number. The energy of the electron is going to be negative. We've got a negative sign in here, and n is a positive number, so the energy is negative. The electron's energy is negative because its energy is lowered by its interaction with the nucleus. As n gets larger, the orbitals get larger, but the difference in energy between them gets smaller and smaller. So it's hard to make visualizations for these things because they're very, very abstract. But we try. So here we're going to make an attempt, and here's energy increasing as we go up. And so we're going to show the energy levels of these different orbitals. And so energy for the quantum level 1 is going to be the lowest. And for hydrogen, that's going to be minus 2.18 times 10 to the minus 18. If we plug 2 into that equation, we find that the energy at this one is closer to 0. So that's a higher energy. And n equals 3 becomes higher, and 4 is higher. And as n increases, the energy level increases. But look at the difference in energy between the levels. It gets smaller and smaller. You see that? The angular momentum quantum number L is also an integer, and it can have values from 0 up to n minus 1. So the values depend on what the principal quantum number is. If the principal quantum number is 3, then L can have values 0, 1, 2, because 2 is 3 minus 1. Each value of L has a particular letter designation, and these are historical. S, P, D, and F. So if L is 0, that's designated as S. L equals 1 is P, D, and F. So these letters are important. Those designate the shape of the orbital. The next quantum number, the magnetic quantum number, specifies the orientation, the direction in space in which these other orbitals are aligned relative to each other. And M sub L also has integer values, and it can range from whatever L is negative to whatever L is positive, and it can be 0. And if we look at how many different M sub L values there are, we get the number of orbitals of that particular shape. So when L equals 2, possible values for M sub L are minus 2, minus 1, 0, plus 1, and plus 2. So there are 5 different values here, which means there's 5 different orbitals that have L equals 2. These numbers specify how the orbitals are oriented. And if all of this just sounds like words, just random words, I totally get that because I feel like that's what I'm doing right now. Hopefully it'll kind of gel together in a few minutes. Spin quantum number specifies the orientation of the spin of an electron. So an electron is not spinning like a top, but we'll be okay if we think of it that way. So Andrew, my youngest, likes to play with Beyblades. Do you know what those are? Little tops, and you pull the little ripcord and the top spins and you battle them in this arena thing. Well, some Beyblades spin clockwise and some spin counterclockwise. And so we can think of electron spin as being like the spin of a Beyblade. It isn't, but it's good enough. So all electrons have the same amount of spin, but they spin in different directions. And so M sub S can be either plus 1/2 or minus 1/2. So it can either be positive or negative. We can think of it as up or down, clockwise, counterclockwise, etc. Okay, so how do we describe an orbital? An orbital is going to have a specific combination of the first three quantum numbers. So if n is equal to 1, L equals 0, and m sub L equals 0, that describes a particular orbital. And we would refer to that as the 1s orbital. You can have multiple orbitals with the same value of n. If n is 3, there's a whole bunch of different orbitals that are possible. All of those orbitals belong to the same principal level because they have the same principal quantum number. Sometimes it's referred to as a principal shell, and that kind of goes back to the Bohr model, where you can look at those different energy levels, those orbits, as being like shells that nest inside of each other, or layers of an onion that you could pull off, right? They're concentric. And so you can think of the energy that way, but the orbitals are not shaped like that. If you have the same value of n and the same value of L, that's a subshell or a sublevel. So here's a diagram that might help. So for n equals 1, the lowest energy level, for n equals 1, there's only one possibility for L. L has to be 0. So L is 0, and if L is 0, there's only one possibility for m sub L, and so there's just one orbital. L being 0 is S, the letter S, and this principal quantum number being 1 gives us the 1. So this is the 1s orbital. There's only one. For n equals 2, now L could be 0 or it could be 1. If L is 0, m sub L has to be 0. If L is 1, now we have three possibilities. It could be negative 1, 0, or positive 1. And so then we've got three different orbitals. This one from m sub L equals 0 is called an s orbital. This is 2s because it's principal level 2. These are also in principal level 2, but now it's called a p orbital because L equals 1 is given the designation p. The third level, we've got L equals 0, so that gives us 3s orbital. L equals 1 is still going to give us 3 orbitals. Those are called 3p orbitals. Now we also have the possibility of L equals 2. If L equals 2, m sub L can be minus L to plus L, minus 2 to plus 2. So minus 2, minus 1, 0, 1, and 2. So then we have 5 different orbitals. These are the 3d orbitals, because when L equals 2, we use the letter D. And I know it'd be easier if it was ABC, but it's SPDF, I'm sorry. Is there anything higher than F? Perhaps theoretically, we definitely won't encounter anything higher than F.
Does 3 go up to F as well? Or?
3 does not go up to F. So in order to get into F orbitals, L has to equal 4. I'm sorry, L equals 3. If L equals 3, then N has to be 4 or higher.
So if N equals 3, L can't equal 3L.
Correct. So N, oops. Gosh. N is things like 0, 1, 2, etc. L can be 0 to n minus 1.
What did you say L represented?
L is the angular momentum. Yeah, angular momentum number. Yes. Thank you. N can't be 0, sorry. There we go. Is that better? principal quantum number, I forget the names of these, angular momentum number, an m sub L magnetic, and m sub S spin. Phew, pulled that one out, barely. So if n is 3, then L can be 0, 1, or 2. If you want L to be 3, then n has to be 4, 5, 6, etc. That make sense? And then the value of L tells us what's possible for m sub L. So that can be from negative L up to positive L, including 0. Any questions? List the quantum numbers associated with all of the 5D orbitals. How many 5D orbitals exist? Okay, so 5D, what does the 5 tell us? That's n. So n equals 5. What does the D tell us? SPD, 0, 1, 2. Right? So D tells us that L is equal to 2. Those are specified by 5D. Now, nothing else is specified, so the next quantum number can be from negative 2 to positive 2. So m sub L could be minus 2, minus 1, 0, plus 1, or plus 2. So you can have an orbital that's n equals 5, L equals 2, m sub L is negative 2. You can have another one that's 5, 2, negative 1, 5, 2, 0, 5, 2, plus 1, 5, 2, plus 2. Yes?
How does L equal 2 when to find L is an n minus 1? So where do you find that?
L does not equal n minus 1. It can go up to n minus 1. Yeah.
And how did you get that 2?
So I got the 2 because we've got S, P, D, and F. S is L equals 0, 1, 2, 3. Yeah.
But it's possible for it to be 4 since it's n minus 1. You don't have a letter for that?
Well, n minus 4, n equals 4 exists, but they are asking us about the 5D orbitals. So these orbitals have n equals 5 and L equals 2 because it says 5D. There are 4D orbitals and 4s orbitals and 2s orbitals. There are all these other orbitals present in that atom, but they are asking us specifically about the 5D.
I meant for L. Like if L, since L is n minus 1, it can be, L can be 4.
L could be as high as 4, yes.
We don't have a set letter for that, like S, E, we don't have a letter for that. Like,
No, we don't.
okay.
Yeah. I think those are more theoretical levels. We don't actually observe them.
So we won't have any of that on the test.
There will be no G's on the test. No L equals 4. No.
And m sub L is equal to the number of orbitals.
Yeah, so the number of m sub L values tells us how many orbitals there are. So if we wanted to list the quantum numbers for each of these orbitals, we'd have 5, 2, negative 2, 5, 2, negative 1, 5, 2, 0, 5, 2, 1, whoops, and 5, 2, 2. It's a little bit like specifying, say, the date, right? So 2018, 3 for March, 14 because that's the day, and there could be 15 and 16 and 17. but there's limits on how many months there are in a year. So, that second number can only be 1 through 12. Can't be 13, can't be negative. And the next number is specified by the previous number. The number of days is specified by which month we're talking about, right? So that's the same sort of notation that we have going on here. So there's 5 d orbitals. Another practice question. Each set of quantum numbers is supposed to specify an orbital, but each of them has one quantum number that's not allowed. Replace that one with one that is allowed. So we have to find the mistake in here. It's a little bit like saying that the date is 2018-13-5. Is that possible? No, because there is no month 13, right? So n equals 3, L equals 3, M sub L is plus 2. So start at the beginning. Can you have n equals 3? Sure. If n equals 3, can L be 3? Nope, it can't. It can only go up to 2. It can only go up to n minus 1. So we have to replace this 3. What should we make it? 2. Could we make it 1? We could, except then when we look at the next one, M sub L is plus 2. If we made L equal to 1, then this wouldn't be possible. That makes sense? Because if L is 1, M sub L could be minus 1, 0, or plus 1. So we fixed that one. Let's look at this one. So n equals 2, that's fine. If n equals 2, can L equal 1? Yes. If L equals 1, can M sub L equals minus 2? No. What are the possibilities for it? It can be negative 1, positive 1, or 0. One of those. You could choose any one. Letter C. N equals 1. If n equals 1, can L equal 1? No. What does it have to be? 0. And if L is 0, can M sub L be 0? Yeah, it has to be. Any questions? Understanding the quantum numbers in itself is not a big deal, but it helps us to understand the electron structure of the atom. So give it your best shot. So how does all of this explain atomic spectroscopy? So the wavelength that we see in a spectrum, the different colors, corresponds to a transition that an electron is making from one orbital to another. When the atom absorbs energy, the electron gets excited. It goes up to a higher energy level, but it's not stable. It's called an excited state. It's like, you give a child lots of sugar and they get all hyper, right? They're in an excited state. Or, you give a grown-up a rock star and they get excited, right? Get all charged up. It's not stable, though. The effect wears off, and then you go back to your ground state. So the excited state has absorbed energy, it's unstable, and eventually that electron's going to go back to where it came from. It could do that in one step, or it might do it in a series of steps, but it'll relax to a lower energy level. When it does that, it will emit electromagnetic radiation. And the radiation it releases, is one photon, will correspond in energy to the difference in energy levels that the electron is moving. So here's the picture. So we've got an electron, and the ground state was in n equals 1, the lowest energy level. This atom received some energy, and the electron absorbed that and jumped up to n equals 3, which is a higher energy. It was up there, it's excited, it's not stable, so it's going to drop back down. It didn't drop all the way back, but it dropped down to n equals 2. When it does that, it releases a photon of light, the energy of that photon corresponds to the energy difference here. Energy cannot be created or destroyed. If the atom absorbs energy, the electron absorbs energy, when it goes to a lower state, it has to release that energy. Now, it doesn't have to release all of it at one time. It jumped up to 3, and it can go back to 1 in 2 different steps, or it could go in 1 step. Any questions? So the reason that we're seeing selected lines from these elements is because there are only particular transitions that are possible. So we only see those specific energy differences. So when the electron is moving between levels, if it wants to go up to a higher level, it has to get just the right amount of energy. It's like getting on the bus and they require exact change. They won't let you pay more. What the heck is that about? I've got $1, it's only 75 cents, but I can't ride the bus. I don't care about the quarter. Take it, and they won't. Exact change only. You have to have the exact right amount. So it'll jump up when it gets the exact right amount, and when it comes back down, it's going to release energy exactly. And that's why in an absorption spectrum, you see dark places, because that corresponds to those energy transition, and that's the electrons absorbing energy there instead of releasing it. So we can predict the spectrum of hydrogen, because hydrogen is simple, and the Bohr model works for hydrogen. So we can calculate the energies of the different orbitals for hydrogen. And we can calculate the spectrum, because if the electron is in energy state n, let's say n is 3, it got excited to energy level 3, then there are 2 places that it can transition to, right? It can go from 3 to 2 or from 3 to 1. If it was in principal level 6, then there'd be 5 places it could go: 5, 4, 3, 2, or 1. So both the Bohr and the quantum mechanical models predict the lines very accurately for hydrogen, which is great and all, but we're interested in a lot more than hydrogen. And we're going to do some of these calculations in lab today. So the energy of a photon, the energy of the photon released, is equal to the difference between the 2 energy levels that the electron went between. It's the final energy minus the initial energy. The final energy is lower. Delta E is equal to the final energy, which would be negative 2.18 times 10 to the minus 18th joules over times 1 over nf squared. That's the final level. And then we're subtracting the energy of the initial. All right, so that was the equation we had earlier. That describes the energy of an electron in terms of a whole number, an integer. So here is the energy for the final position. So this is the final n. This is the energy for the initial, and we're just subtracting them. So you can simplify that a little bit by factoring out the 2.18 times 10 to the minus 18th joules. And so you get this equation right here. The change in energy for the atom is going to be opposite in sign to the change in energy for the photon. The atom is experiencing a negative change when it emits energy, because energy is going out, right? The electron's falling from a high level to a low level. The change is going to be negative. But the photon that is released has positive energy. we also have this equation where the wavelength is equal to hc over lambda, hc over E. So the energy of the photon is described here in terms of the wavelength and the speed of light. So this is for hydrogen. And so this shows all those different transitions. So you can add energy and put the electron up at one of these levels. If you give it way too much energy, you actually ionize the hydrogen atom, and the electron completely leaves. The visible light transitions fall here from 5 to 2, 4 to 2, and 3 to 2. Those are within the visible region. You can have 5 to 3 and 4 to 3. Those fall in the infrared. Those are below the visible, below the red. And then these 5, 4, or 3, 5, 4, 3, or 2 down to 1, those are ultraviolet. Those have more energy. And so we can't see those with our eyes. Any questions? So determine the wavelength of light absorbed when an electron in a hydrogen atom makes a transition from an orbital in which n equals 2 to an orbital in which n equals 7. So which of these is the initial level? 2. So the initial, because it's starting there, is initially in level 2, and the final is where it ends up, is 7. And we're asked to determine the wavelength of light. So we know that the wavelength is equal to hc over the energy. H and c are constants, but we need to figure out what the energy for this is. So the energy of the photon is going to be opposite in sign to the energy for the atom, and is really the change in energy. So the change in energy for the atom is negative 2.18 times 10 to the minus 18 joules times, it's always final minus initial, 1 over an f squared, so that's final, 7 squared, minus 1 over the initial squared. So we can calculate that. Negative 2.18 EE minus 18 times the quantity 1 divided by 7 squared minus 1 divided by 2 squared, close parentheses. And so this is 5.005 times 10 to the minus 19 joules. So this energy came out positive. The atom is absorbing energy, right? Determine the wavelength of light absorbed when an electron in hydrogen makes the transition. So this is absorbed. The energy of the photon is going to be opposite in sign to the energy of the atom. So the energy of the photon is negative because the photon is going into the atom. But if we put in E as a negative number, we're going to end up with a negative wavelength. Is that possible? No, it's not possible. So we need H, 6.626 times 10 to the minus, is it 36? 34, thank you. I didn't think that sounded right. 34 joule seconds. And the speed of light is 3.00 times 10 to the 8th meters per second. And we're going to divide by this energy. The units are a little friendlier here. Joules cancel, seconds cancel. We're left with meters, which is an okay unit. 6.626 times 10 to the minus 34 times 3 times 10 to the 8th divided by 5.0051 times 10 to the minus 19. 3.97 times 10 to the negative.
Where did the 3.0 times 10 to the 8 come from?
That's a good question. That's the speed of light. So this is h, it's a constant, and this is c, also a constant.
So H and C are always constant, so and we just need to figure out the energy.
Right.
And the wavelength.
Yep. H and C are always constant, so if you know the wavelength, you can calculate the energy. If you know the energy, you can calculate the wavelength. So we can calculate the energy of the transition, but then we don't know anything about where the electron is.